Shalom. Shalom a todos. Espero que hayáis... shalom to everyone. Sorry, I forgot I was doing this in English. I hope you all arrived well from the other page where this was pretending like it was going to air. So here we are. There's a silly globling in the chat. Hugo Perez. Bad for you, man. Bad for you. Now, let me just sort Windows out. Oh, very bad. Okay. I'm still figuring out how to use this new system. So first, we're going to play. What the heck is... all the windows have resized. Okay. Just bear with me while I resize Windows. And this is how to embarrass a globling. It's quite apt that there's a globling in the chat who doesn't mind being embarrassed, like he was embarrassed by me the other day. But one of the answers to the question of how to embarrass a globling is you can't embarrass a globling, no matter what you show them. So first, I'm going to share this screen. Let me see where's the screen that's sharing? Share screen. Okay. Okay. So where is it giving me the option? Opera. Got it. Here. Okay. Hopefully I'm sharing this right now. Let me just go and check. Dagnabbit. Yes, I am sharing this. Great. We're going to play just a portion of this. The video, mechanical gyroscope, detecting drift, Stefan P. Magnetic field test. It's not just the magnetic field test. It's a whole video about drift. Wonderful. We're just going to listen to a few seconds, then I'm just going to make a small correction. And I don't understand why people who do have quite advanced understanding of gyroscopes don't get what I'm about to show. So let's listen carefully. Volume up. Yes.
The shaft of the flywheel was pointed to north.
The shaft of the flywheel was pointed to north. That's the small thing there in the center. That was pointing to north. Very good. And?
If there would be an earth drift.
If there would be an earth drift, in other words, if the earth was rotating,
flywheel would not tilt.
And the flywheel would not tilt. I'm going to play that again, just so we all hear.
The shaft of the flywheel was pointed to north. If there would be an earth drift, the flywheel would not tilt, and therefore would not interact with the z-axis reading.
Okay. So now we're going to see about that. Just give me a second. Nabbit these windows. Okay. Take that in. It's playing the role of a globe. This is playing the role of a latitude, and this is the same latitude 6 hours later. 12 hours later. Okay? The same latitude. Earth's axis, equator. I've not gone to 48 north, which is where he was, because it becomes very indistinct over here. What becomes indistinct? Well, think about this. This is a gyroscope's shaft pointing to north, which on a globe would be perpendicular to a plumb line. Okay? Pointing north, not just pointing that way along with the Earth's axis. It's not an equatorial mount. It's not like this, aligned the same way as Earth's axis. If it was, then it would be leaning down on his desk. So the shaft would be leaning down on his desk. Okay? Good. It isn't. Here's his shaft, which is oriented to the north. Great, that's fine. 12 hours later, that shaft would be like so. This is what rigidity in space means. This is how it would be. Okay? They're supposed to be parallel. I've just done it by eye now. Not quite parallel, but you know what I mean. So please consider that when doing further gyroscope tests. Okay? Okay. Now, on with the... What the heck is this? What is this thing that has appeared? Huh? Oh, interesting. The screen stays there. That's very interesting. That's good. Good. Okay, so that's that. I can close that. Come on, don't trick me. Okay, close this. Now we're going to discuss further globe problems. That gyroscope test showed drift. Unfortunately, it didn't quite show drift like it should on a globe. Sorry, I'm now setting up Windows because everything has resized very strangely. Anyway, right, so let me share screen again. The screen has gone, dagnabbit. I had a screen there that was ready to share and it's gone. Okay, so get that off there. Okay, Okay. I showed this the other day. There. I'm just going to play this. I'm going to slow it down. Okay, so there. Okay, see what I mean about things resized? That's very weird, but hey, still learning. Right, we're going to see a huge distance between, well, South America and Africa, and a very short distance between Australia and South America. Considering that this is the globe, and they've known it was a globe for more than 2,000 years, apparently. Well, they've had to tweak things relatively recently, considering that they've known about it for 2,000 plus years. Good gosh. There's Australia. Now keep watching out for South America. Dun, dun, dun. How far away will it be? There it is. Oh dear. Okay, so now I share another window. Give me a second. And then we're going to go to, we're going to show, because the best way to embarrass a globling is by showing them their own supposed info. Okay, so we're going to show cosmology, globe cosmology. Now, what do I have here? See, that logo, that was the Universal Pictures logo. Okay, well, this isn't a Universal Pictures logo. This is a Masonic Lodge in Cuba with an even bigger distance between South America over to the left and Africa. Huge distance. If you take these to be 15-degree separation between the segments, which is pretty much what it's showing, well, that would be 1, 2, 3, 4, 5, 6 hours. No, wait, from Greenwich Mean Time, 1, 2, 3, 4, 5, 6, 7 hours to Buenos Aires. That's interesting. Oh, and there's Australia. You see all the Indonesian Isles all just sticking down towards Australia. It's interesting. And there's another shot just to see the great big Atlantic Ocean, just like not shown on maps today. So now we look at a map, also from the Masons. Oh, this looks like more like the map today, but wait a second. Wait a second. See this black line there? I placed that there. What for? So you can see just quite how close, in terms of longitude, Western Africa would be from Eastern Brazil. What's that? About 4 minutes? No, less than about 3.5 minutes, 3 minutes. In terms of rotation or globe sun illumination, can you see? Less, that'll be about a minute actually. But good gosh, what the heck's going on? First they show us great big gap between the two, then they make this, and remember, I placed that dark line. 2,000 years, and they keep having to tweak. It's embarrassing for the globelings, but you can't embarrass a globling. You can't embarrass them. Wait, let me make sure I'm actually showing what I think I'm. Yes, I am showing what I think I'm showing. Oh, and you see the cursor too. Good. So this here, that's the distance. Let's see again. Okay. Western Africa here. What's the distance between there and that longitude? Tiny distance. That's right. Well, let's look at this globe. Let's look at the distance there. Good gosh, great big distance. Here's Western Africa. Here's Eastern Brazil. Good gosh. Big problems for the globe. And now we're going to show even more problems, this time from their cosmology. So let me close that. And then whilst I'm showing this, I'm going to join you in the chat. That's going to be fun. Okay, I can close that. So it wasn't just bad artists for Universal Pictures who just made a globe, didn't pay attention to distances between things or anything like that. No, they made a globe based on what globes looked like at the time. Okay. Now we're going to watch Why Can't You Go? No, wait. Let me see which one I have linked first. Wait a minute. Yes, okay. Sorry. This is a new system that I'm using. How to travel faster than light. And whilst I'm playing this, I will come and join you in the chat. Hopefully everything will be fine, even though I'm going to play this and go and join you in the chat.
I mean, I totally want to know how to go ludicrous speed, but unfortunately, and I hate to have to tell you, these are all fiction. So if it's possible to go faster than light, what exactly do I mean by the speed of light? I mean the speed of light in a vacuum in a location where space-time is not bent or changing.
Oh.
Under those conditions, the speed of light is about 186,000 miles per second, or...
Did you see that? I mean, this is all fantasy, okay? But let's go back. Under what conditions? Flat and unchanging space. Oh, okay, interesting. Let's continue.
For the metric crowd, precisely 299,792.458 kilometers per second, or fast enough to circle the globe 7.5 times in a single second. Light is like really, really fast. When physicists use the symbol c to denote the speed of light, it's this speed that they're talking about. So how can you go faster than light?
How can you go faster than light? Now he's going to explain things that are, well, contradictory to reality and to their own theories. And we'll see him contradicting them later on. But you see, even if you show the globelings this, they still won't be embarrassed.
I can think of 3 examples, although they all aren't quite what you probably think. The first is cheating. When light enters a transparent medium like water or glass or something, it slows down. In glass, light travels at about 2/3 the speed it does in a vacuum. In water, it's about 3/4. You can see the effect of this change in velocity by simply sticking a pencil in a glass of water. The pencil doesn't really bend, but it appears to because of this effect.
It's not bending because of the speed of light. It's bending because of the angle. So if there's an angle change, there would be a speed change. Like, you don't understand light. Stop talking about things you don't understand, Mr. Physicist.
While light slows down in the transparent medium, other particles do not. That means that if you shoot an electrically charged particle like an electron or a muon traveling at near the speed of light at that same medium, the charged particle travels faster than light in the medium. Cool, huh? When this happens, the charged particle emits blue light like you can see here. This light is called Cherenkov light after its discoverer, Pavel Cherenkov.
And what's happening is that light is just a traveling faster light. That's why it's blue. Yeah, no other explanation necessary. Let's continue.
Explaining just how Cherenkov light is formed is, well, tricky, and maybe I'll make a video about that. But the blue light that you see here proves that it's possible for objects to move faster than light in a transparent medium. In this example, the light is formed when radioactive material emitting highly energetic particles is immersed in water. It's all way cool. So that's maybe a cheat. Particles move faster than light, but it's not because particles got faster, but because light got slower. Are there?
And are those real particles, or are those insubstantial particles, like ghost particles, like particles without mass and matter? Don't know. Let's continue.
Any other examples? Well, there is another instance of information traveling faster than light, which I'll mention only briefly, and this involves a topic called quantum entanglement. Quantum entanglement is a category of quantum mechanics, which is known for its bizarre predictions, cats both alive and dead and all that.
Okay, Schrödinger was wrong. And at the time, philosophers were saying, this is cockamamie, this is not true, this is logically impossible, and therefore not true. You cannot have two mutually exclusive states coexisting. But they need it for the cosmology. Oh, then it's possible, I suppose, if it's necessary. You know, just like Santa Claus or Hugo Perez's intelligence, you can create something that doesn't exist and say that it exists.
It's not possible to explain it in detail here. That would actually require not just one video, but an entire series. But here, I can give the highlights. In quantum mechanics, probability rules. Anything that is possible can happen, governed by...
And anything that is not possible can be made possible just by talking about it as if it was possible. There you go, that's easy.
By the probabilities of that particular situation. As an example, a subatomic particle can have a spin of plus or minus. You can't know which of those...
Now, remember what I said about the needed Schrodinger's cat? You know, both alive and dead. And you don't know until you look. This is why.
Spins it has until you actually measure it. It's important to understand that
there seems to be a big important thing about what happens when you resolve it through measuring it. I'm going to play it again.
Of plus or minus. You can't know which of those spins it has until you actually measure it.
Now, here's an important thing. Can you know the weight of an object before you measure it? Nope. You can know it after. In fact, you won't know it until you measure it. Does that mean that it has a whole series of different weights, or even that it has two different weights? Is that what it means? But you see what they're doing? They're saying there's an important critical thing to you measuring it. That's when it coalesces and becomes either positive or negative. Like, oh, really? Should we do the same with weight? Should we do the same with family? Should we do the same with everything in the world? Should we say we can't make any deductions about that thing whatsoever until we measure it, and then the measurement has a knock-on effect that makes the measured object what it appears to be? Listen.
It's important to understand that this isn't a simple case of ignorance. It's not that the spin is plus or minus and you just don't know.
Yes, it is. The spin is either plus or minus. The cat is either dead or alive, not dead and alive or plus and minus. Do you see? This is why the philosophers were saying these guys are full of nonsense. Yeah, they're saying that I think I mean two mutually exclusive states, as if the words mutually exclusive didn't have any meaning. It is one or the other, and you can't tell which until you check. I'll show you with a trick where you hide a coin in one hand and you don't know where it is.
It's both plus and minus, and it becomes plus or minus when you measure it.
See, the act of measuring causes this resolution. It has a causal effect where you're measuring it. Well, it makes it either be plus or minus. It's like, no, wait, it was plus. You measured it and it said it was plus. Or it was minus. Notice that I said or. And you measured it and it was minus. Or is the important thing there. But you can't have concrete things like that in the cosmology of the globe, because the whole thing goes to pot if you have concrete things like, I don't know, possibilities versus impossibilities. So you have Schrodinger's cat. There you go. Yeah, see, Schrodinger, he said, if you put a cat in a box, right, and there's a poison vial, right, and when you close the box, that poison vial might or might not break. You don't know. And it will either kill, if it breaks, it will kill the cat. But if it doesn't break, it will not kill the cat. And you don't know what's happened until you open the box. But until you open the box, the possibility is that it has killed the cat, or, well, and that it has not killed the cat. Therefore, the cat is both dead and alive. See? That's how you can have something that's plus and minus.
Now, suppose you take two particles and set them up so that they have opposite spins. If one is plus, the other is minus, and vice versa. When physicists do this, they say that we've entangled the two particles. You can't know in advance which particle is plus and which is minus. You then separate the two particles by a large distance and look at one of them.
Sorry.
Say you find that it's a...
I have to just... I don't understand. Well, I do. It's through stupidity. Through the stupefyingness of education. He just said, I'm going to play it again.
The other is minus, and vice versa. When physicists do this, they say that we've entangled the two particles. You can't know in advance which particle is plus and which is minus.
That's a retarded thing to say. You can't know in advance. Yeah, fine. And what's that got to do with the rest of the gibberish you're saying? You see, so they add that, which is true. You can't know in advance. If you don't know in which drawer there's a pair of socks, you can't know in advance to checking. You check and say, oh, it was in the bottom drawer. There you go. Now you know. But before you did that, you didn't know. That's a truism. That's true about life and reality and existence. So they tack that in at the end of a gibberish Schrodinger multi-existent layered situation. So you see what they did? They just talk gibberish, and you can't know before you measure. But yeah, you also can't taste before you put it in your mouth. Stupid.
You then separate the two particles by a large distance and look at one of them. Say you find that it's a plus spin. If you look at the other particle, you'll find it's a minus spin every single time. And this will be true even if you look at the second particle so quickly.
So you look at one brick and it's red, and you look at the other brick and it's blue. And this will happen no matter how quickly, listen,
that you see it before a signal arrives from the first particle traveling at the speed of light.
I'm going to play that again.
And this will be true even if you look at the second particle so quickly that you see it before a signal arrives from the first particle traveling at the speed of light.
So, one brick is red, the other brick is blue. But you see, because what we're trying to tell you is, if this brick is red, then the other one is blue, okay? And the other one is blue because you determined that this one was red. So the blueness is projected quantum entanglement style to the blue brick so that it gets there even before you can quickly look around, even before the information can have arrived. It's like, moron, that brick is red and the other one is blue. It's really simple.
Einstein called this a spooky action at a distance.
That guy was a retarded guy, Albert Einstein.
And it says that the information in quantum mechanics can travel faster than light. Nobody understands this, but it's well established and it's just a true effect. So that's a case of something traveling faster than light, but you can't use it to send a message, and it's still not the same as an object moving faster than light, like the Starship Enterprise or the Millennium Falcon. So let's talk about a third situation where things actually can travel faster than light, and that's the expansion of the universe.
Now, this is where I'm going to make something very clear to everybody listening. Globling and flat earth are alike. Let me change this. Oh, dagnabbit. I see what's happening. There I am. Okay. What is space? Because some flat earthers say space isn't even real. Yes, it is. Don't say that, because people are going to think you're very, very stupid. What you mean is the space that's been created for the distance between stellar objects, that's not real. Great. Just like the globe Earth isn't real and the globe sun isn't real. Great. But what is space? Because it is a thing. There's space in my cup. There's space in my ashtray. There's space where I'm living. Space is distance that's available for something to fill it. Distance. Okay? Space is distance. That's what space is. It can be full or it can be empty, but it's still distance. Okay? Great. Now listen to what he's going to say about space, which is distance, traveling faster than the speed of light.
Now I should be cautious. When you hear people saying the universe expands faster than light, it's obviously a statement that requires some care, because your first question should be, what does that mean? Well, obviously, the universe can't mean our planet, our solar system, or even our galaxy. After all, none of them are expanding much, if at all, and certainly not at the speed of light. In 1929, American astronomer Edwin Hubble combined measurements taken by several people and found that
distances, listen,
galaxies are moving away from Earth, and the
distances between galaxies. So distances, that distances were growing were longer.
The further away they are, the faster they're moving. This is now understood to be evidence that the universe is expanding. Using modern numbers, a galaxy a megaparsec away is moving away from us at 70 kilometers per second.
Says who? Well, says people who like doing long, complex math. That's who. Oh, okay.
A megaparsec is a million parsecs, which is 3.26 million light years, by the way, but astronomers use megaparsecs, so I will too. If a galaxy a megaparsec away is moving away at 70 kilometers per second.
Wait, let's go back. Remember, light years is distance, not time. Distance.
Moving. This is now understood to be evidence that the universe is expanding. Using modern numbers, a galaxy a megaparsec away.
See? What away? A certain amount of distance away. All right, so a parsec really is distance, yes. And that's, those parsecs are like millions of light years, yes. Great. Distance, big distance, got it.
Is moving away from us at 70 kilometers per second. A megaparsec.
Moving away from us. What does that mean? It means the distance between us is increasing. The distance. I'm saying this on purpose.
Is a million parsecs, which is 3.26 million light years. But
that's a measurement of distance, of cosmological gibberish distance, but it will still be actual distance. Okay?
By the way, but astronomers use megaparsecs, so I will too.
Great.
If a galaxy a megaparsec away.
If a galaxy a certain distance away
is moving away at 70 kilometers per second.
Is moving away. Well, then it isn't a megaparsec away, is it? Because it's, well, no longer 1 megaparsec. Oh, right. How long now? Oh, look, see? It's a gibberish, but let's continue.
A galaxy 2 megaparsecs away is moving away at 140 kilometers per second.
Oh, wait, that's 2 times 1 megaparsec.
3 megaparsecs means 210.
Hey, that's 3 megaparsecs. Oh, very complicated.
Kilometers per second, and so on. So we know that the speed of light is 300,000 kilometers per second.
No, you don't. Dim.
So we can figure out how far away we have to go to have a galaxy moving away from us at the speed of light.
So we can use that to figure out how far we have to go to have a galaxy that's moving away from us at the speed of light. Well, by multiplying those parsecs, well, how far away, what would the distance be to the point where from us a galaxy was traveling that fast? Wait a second. What about that galaxy and other galaxies around it? How is it moving away from us at that speed and not around other galaxies that might be traveling at the same speed as ours? Relative, could be parallel, on a parallel path to us, but right next to that parsec mega fast other galaxy, reaching the speed of light speed galaxy. Moving very fast away from us, speed of light, but not fast away from that other one, the speed of light, because that other one is like, it's not moving away, it's just parallel. It's Methuselah. That star, that's the one.
That turns out to be 4,296 megaparsecs, or just shy of 14 billion light years.
Right. That's how far a galaxy would have to be traveling at the speed of light. 14 billion light years. Okay.
This means that the surface of a sphere centered on the Earth and with a radius of about 14 billion light years is moving away from us at the speed of light.
No, it doesn't. It doesn't at all. You could have a static sphere that distance away from us and it not be moving at all. Why wouldn't you? What's making it be moving? What's giving it its movingness? What's giving it its energy to be moving away? No. Oh, no. Oh, no. Well, because we said it is. Oh, is that how it works? Yes. Schrodinger's cat, remember?
It also means that bigger spheres are moving.
It means, like this is true. It means this. Well, look, there are presents under the Christmas tree. It's Christmas morning. It means Santa Claus left them.
Away from us at faster than light. A sphere with a radius 28 billion light years across is expanding at twice the speed of light. So what does this mean?
It means the speed of light is not a constant if things can be traveling at twice the speed of light.
Does it mean that there are galaxies moving away from us at speeds faster than light? Yeah, it does.
I'm going to play that again. Because even if you play this over and over to a globling, he'll just go, yeah, and? Listen.
The speed of light. So what does this mean? Does it mean that there are galaxies moving away from us at speeds faster than light? Yeah, it does. Of course, it also means that we can never see them.
See? Does this mean that little elves made the toys? We can't see what made the toys. Therefore, it must be the little elves that made the toys.
If objects move away from us faster than light, then that means that light emitted by them can never get to our eyes.
Like, you see how you can't see anything there? Yeah, it's because there is something there, but it's moving away so fast that you can never know that it's there or even was there at any point, because it will always be farther and farther away. Then how do you know it was there? Oh, we said it was, that's why.
So we can never see light emitted by anything currently further away than 14 billion light years.
Or according to your cosmology, because that's older than your universe. I know you're dumbing it down, but could it be because age of the universe thing?
The true number is a little different because of details of how the expansion speed has changed over time. To get the number right means we have to take a more nuanced approach than I'm doing here. But those details...
Oh, you said the word nuanced. Oh, you mean a more specific approach? Oh.
Really don't change the big message.
The big message? When you're looking into blackness of the night sky, sometimes you'll be looking in the direction of galaxies moving away faster than the speed of light, which means they're farther away than the age of the universe allows them to be. See, that's how we get around that problem.
It's also incredibly important to be super careful about how we envision it.
You have to be super careful about how you imagine it. You don't want to imagine it the wrong way. You might end up in Sauron's lair. What? Oh, be careful how you imagine it. Imagine it.
The reason is that it's not precisely accurate to say that these galaxies are moving away from us faster than light.
So, you know how he was just explaining how those galaxies are moving away from us faster than the speed of light? Well, be careful, because those galaxies are not moving away from us faster than the speed of light. That's right. I'm going to replay this whole last minute or so.
14 billion light years. This means that the surface of a sphere centered on the Earth and with a radius of about 14 billion light years is moving away from us at the speed of light. It also means that bigger spheres are moving away from us at faster than light. A sphere with a radius 28 billion light years across is expanding at twice the speed of light. So what does this mean? Does it mean that there are galaxies moving away from us at speeds faster than light?
He just said, does it mean that there are galaxies that are moving away from us faster than the speed of light? And listen to his answer.
Yeah, it does.
Yes. Yes, it does mean that galaxies are moving away from us faster than the speed of light.
Of course, it also means that we can never see them. If objects move away from us faster than light, then that means that light emitted by them can never get to our eyes. So we can never see light emitted by anything currently further away than 14 billion light years. The true number is a little different because of details of how the expansion speed has changed over time. To get the number right means we have to take a more nuanced approach than I'm doing here. But those details really don't change the big message. It's also incredibly important to be super careful about how we envision it. The reason is that it's not precisely accurate to say that these galaxies are moving away from us faster than light.
That's right. That's called gaslighting. Yeah. When somebody says, I love you because I hate you. I hate you because I love you. Oh, yeah, I put the book on the table because I put the book on the shelf. Yeah, galaxies are moving away from us faster than the speed of light because they're moving away from us not faster than the speed of light. They're not moving away from us faster than the speed of light because they're moving away from us faster than the speed of light. I'm going to play that again for the imbecile globelings.
Further away than 14 billion light years. The true number is a little different because of details of how the expansion speed has changed over time.
This is just
to
padding.
Get the number right means we have to take a more nuanced...
All of this that he's saying now is padding. Otherwise, he'd be saying, so, a sphere this distance, 14 billion light years, faster than the speed of light. However, not faster than the speed of light. And people say, dude, you're talking nonsense.
Approach that I'm doing here. But those details really don't change the big message. It's also incredibly important to be super careful about how we envision it. The reason is that it's not precisely accurate to say that these galaxies are moving away from us faster than light.
Despite that being what he just said, I think it's 30 seconds ago.
Yes, the distance between us is increasing, but it's...
Yes, the distance between us is increasing, which means the space between us is increasing, but
it's because space is expanding.
yes, that's distance between. Never mind expanding. You haven't got a measuring tape that's getting stretched. It wouldn't be a very useful measuring tape if it was elastic. It's not expanding. You haven't got a clue what you're talking about. You're talking about distance between objects growing.
Not because the galaxy is moving away in space.
No, false. Even if space is expanding, it is moving away. That would be, well, distance between growing, whether space or any other maverick term. The distance is moving away from us, or the distance is static and we are moving away from it. It doesn't matter. It's still the distance between is growing. That's what he's saying. But now he's saying, but, however, watch this.
It's kind of like putting a rubber duck in a river. The duck isn't moving as far as the water is concerned.
The duck isn't moving as far as the water is concerned because in that frame, the duck isn't really moving. How can you tell that, Antonio? Because I can see the trees that are reflected in the water. It's not moving. Let's see what happens next.
It's the water.
Oh, look. Now they've put it in a river where it's moving. And saying, yeah, remember when we showed you the duck and it wasn't moving? There's the duck, look, see? Ah, quick, next scene.
Water that's carrying the duck away.
This is how they explain these things to the retarded globlings who never stop to think. They don't stop to think.
Space.
Can you see how that duck is in a very peaceful little pond? It's not moving anywhere because it's not even in a river. Okay, and you can see because it stays in the center of the frame, even though it's zoomed in rather a lot. Okay, and you can see the trees and the leaves and whatnot in the background, right? I'll hit play. Watch.
It's kind of like putting a rubber duck in a river.
That's not a rubber duck in a river. That's a rubber duck in a pond.
The duck isn't moving as far as the water is concerned. It's the water that's carrying the duck away.
Oh, it's very interesting. Hey, what happens? Let's go back and pretend. Let's go back and pretend that this duck was on that river. And somehow, you know, due to parallax and whatnot, the distant trees that are reflecting in the water, that they just appeared to be there, okay? And what was really happening was the camera was moving very fast at the same rate as the duck because the water was carrying the duck further down the stream. Would that mean that there was no distance growing between the observer and the camera? No. Why not? Because the duck's flowing down the river, that's why. If the camera's keeping up with the duck, then it's moving down the river too. We're not talking about somebody just on a gurney or on one of those movie tracks for a camera. Oh.
It's kind of like putting a rubber duck in a river. The duck isn't moving as far as the water is concerned.
Right. The duck isn't moving as far as the water is concerned. Now we're going to skip that little tricksy little NLP image that they showed. We'll go to here. Okay, so what's happening here?
It's the water that's carrying the duck away.
It's the distance between the observer and the duck growing. Yep, great. That's all we needed to know.
Or like drawing dots on a balloon that's inflating.
Ooh.
The dots don't move on the surface of the balloon, but the distance between them is increasing because the balloon is stretching.
Right. Did the dots move?
Or like drawing dots.
Okay. Now we're going to look at pick an individual dot and see whether or not it moves.
Dots on a balloon that's inflating. The dots don't move on the surface of the balloon.
All of them are moving, which means distance changing.
But the distance between them is increasing because the balloon is stretching.
Never mind that. Distance increasing. That's what I've been saying all along. Thank you.
So it's entirely fair to say that...
You see? So You know how we showed you that duck in a pond and we told you it was in a river, and then we showed you it in a river and said, see, relativity, change of perspective. See how it's moving really fast. It looked like it wasn't moving at all, but now look, it's moving fast. Like, right. So it's now perfectly fair to say, is that what he said?
The surface of the balloon, but the distance between them is increasing because the balloon is stretching. So it's entirely fair.
So it's entirely fair to say
that there exist galaxies that move away from us.
Whose distance from us increases
faster than light, but only in the sense that the expansion of space makes it happen.
Okay. Are they moving away from us faster than the speed of light? Yeah. Okay, that's all we need to know. Is that possible? Nope. Oh, okay.
Those galaxies are stationary, or at least nearly stationary, with respect to their own space.
But the distance between us and them is growing, which means, well, speed. Never mind. He's like, oh no, the thing is stretching. It doesn't matter. It's still speed, distance, and speed.
They're not moving through space.
They're not moving through space. What are they moving through? Nothing. Are they moving? No. But I thought you just said that they were moving. Of course they're moving. Wait, what? Huh? You just said no when I said, are they moving? No, I didn't. Yes, you did. You just said that they weren't moving. Well, they're not moving. Well, so they're not moving. No, don't be stupid. Of course they're moving. And so on.
I've described 3 examples of the phenomenon.
Now, it's just talked gibberish for 10 minutes.
But none of them are something that those of us who hope to explore the cosmos would like to see.
And all of us who hope to explore the cosmos are going to do so from our little offices with our eyes closed sometimes, seeing all that blackness and all that distance that's not distance, that's just space, but no distance. And we're going to explore it in our brains.
According to our best understanding of the laws of physics.
Ha! The best understandings of the laws of physics. Yeah, where a cat can be both dead and alive.
Light obeys the ultimate speed limit. Now, our understanding of the rules that govern the universe are constantly improving, and it's okay to hope that we'll...
Right, so according to their best understanding, but it's constantly improving, so getting to better understanding, which says that that previous understanding was wrong or a bit facile or just a bit shoddy or just, a bit broken, a bit crackpot.
We'll discover some new principle that makes it possible to go faster than light.
Oh, like wormholes or something, I don't know.
Although unlikely, it may be that we will eventually find some new phenomena that changes our prospects for exploring the galaxy.
Oh.
And then, and only then, we will finally have figured out a way to go.
Very funny. So, that was how to travel faster than light. Now we're going to watch why you can't go faster than light, explained by the same fella. And some of you have seen this before because I showed these before, but I just wanted to show them again because you should see the comments from the Globelings after any hangout that I do regarding these things. They go nuts. They really object to people mocking their religion. Like they really object. You just don't understand. It's like, no, I understand. I'm explaining to you that you're retarded. You're not understanding that.
For the past 100 years or so, scientists have pushed our understanding of the universe into some extreme conditions.
No, that's not understanding. They pushed fantasies into extreme conditions. Great. Yeah. Look, dude, Gandalf fell for an age fighting the Balrog. That was extreme. Wasn't real, but still, it was fascinating, and it happened in that story. The story of physics, really extreme things. But no, it's fantasy, silly.
For example, the world of the very small, the realm of very high speeds, and under the frigid conditions of near absolute zero.
Ooh.
While each of us have developed an intuition about how the world works, it's very important to remember that this intuition only applies to a very limited set of conditions. For instance, there's absolutely no reason to expect that matter will act the same in the center of the sun as it does here on Earth on a bright and sunny day.
There's no reason to expect matter to behave the same in your mouth while you're chewing it as it does in your large intestine. Oh, that's fascinating.
However, that last statement is hard for some people to accept, and
No, it isn't. It's quite easy.
judging by my email inbox, the extreme realm that causes people the most difficulty is what happens when things are going super fast.
Super, super fast. Like faster than fast.
In 1905, Albert Einstein published.
Look, somebody brushed his hair. It's before they decided to go with the crazy hair, you know, to kind of mesh a bit with Tintin. Yeah, with a professor there, sometimes having messy hair. Yeah, no, so they brushed his hair. Look here. Gonna go play now on my bicycle. Yes, go on.
Published his theory of special relativity. It predicts all sorts of mind-blowing things. For instance,
By the way, Einstein didn't write that. That was written by Maitre and team. Same as the stuff that was published from Hawking after Hawking became disabled. Yeah, it wasn't written by him.
Since distance shortened and clocks slow down. I made another video about how clocks act at high speed.
Hey, distance shorten and clock slow down. Hey, you know when you're 10 yards away from your car and you carry on walking, the distance between you and your car shortened. And the amount of time it was going to take you to get to the car, which was like 10 seconds, okay, well, it got shorter too. Good Lord, fascinating.
It turns out that all of those seemingly crazy implications.
Remember, whenever a physicist or a cosmologist says it turned out or it turns out, they're just talking gibberish. They're just trying to make it sound like it's something true.
Originate from a single cause, or maybe two if we take it slow.
So there's one cause, but if we go two, there's two causes. That's right. Just like at the cinema, you might pay for one ticket, but if you really take your time, you might get to watch two movies.
So first, let me tell you what this video isn't. It doesn't tell you about the postulates that Einstein used to build his intuition, and it certainly doesn't derive his equations.
What do you mean by postulates? Ideas. Oh, right, okay.
Instead, this video tries to tell you the key insights that make it easier to develop a relativistic intuition.
Oh, a relativistic intuition. What would that be? Would that be kind of conditioning? Yes, that's right.
I hope to teach you why it is impossible to go faster than the speed of light.
Ha! Unfortunately for him, I just showed the video of him saying how to go faster than the speed of light.
If you're not a physics groupie,
Wait. How can you go faster than the speed of light? You can surf like the Silver Surfer on a wave of gravity, a gravity wave. Just surf, whoo. And yeah, the more distant you are from planet Earth, for some reason, the faster and faster that you're going. That's right, because if you're only 1 parsec, then, and if you're 3 parsecs, and oh, good gosh.
hearing that there's a maximum speed in the universe might surprise you, but it's true.
But it's not true. It's true unless you say that it isn't true, in which case it isn't true. See?
And if you are a groupie, you've probably heard that the reason that you can't go faster than light is due to the fact that mass increases when you speed up.
Oh, if you're a groupie. Okay, let's listen some more.
It turns out that the explanation
Oh, it turns out again.
of mass changing as you go faster is a wrong one. I know that statement is going to confuse some people, including those with fairly sophisticated understandings of relativity.
Including those who read A Brief History of Time, where Stephen Hawking explains that that's an absolutely necessary quality for anything to travel at the speed of light. Yeah. So see that those squiggles on the board, that's him proving that Hawking was wrong. He's just not mentioning it.
But it's true. However, that then leaves an open question. Just why is it that you can't go faster than the speed of light?
What if you surf on a gravity wave? Can you go faster than the speed of light then? What if you surf on cosmic background radiation?
It turns out to be due to a combination of a deep and fundamental property of the universe and fairly simple geometry.
What's that property?
So let me explain how that all works. The first of the two crucial insights is that Einstein taught us that space and time are not separate entities, but rather they are two components of a bigger idea called space.
Okay, I explained this in the Book of the Sun. Two components of the same thing. You know, like blue jeans. They have blueness and they have cotton making the jean. So the blue jeans will be the jeans. Okay.
Space-time. I'll give you a helpful visual way to think about this in a moment, but for right now, just trust me on this.
Just trust him. Okay, so blue, we could say blue is space, and the fabric of the blue jeans is time, and the both of them together make blue jeans. Or if you want, you could just say jeans and not even say blue. You could say that threads going down, those threads, space, and threads going sideways, those threads are time. See? So what's the fabric made of? It's made of, well, jean. Oh, right, I see. So the jeans are made of jeans. Yeah, it's so the cotton fabric is made of cotton. Yeah. Oh, that's interesting. So the space-time is made of space-time. Yeah. Oh, well, that makes everything clearer. What? Look up the definition of a circularity. No, I'm not looking up a definition of a circularity.
Then we need to combine that insight with the observation that everybody sees the speed of light to be the same.
Right, so let's go back to that insight. So the clever insight. You know, distance, yeah. Do you know what distance is made of? Well, space. No, it's made of space and time. Okay, is it really? Yeah, I think you're wrong. I think there can be space without time. I'm here, mountains are over there. Time is ticking for me here. Time is ticking over there too. The same time ticking over there. If I travel, none of that's going to change. All that's going to change is, well, that I'm traveling through space.
Taught us that space and time are not separate entities, but rather they are two components of a bigger idea called space-time.
Wow.
I'll give you a helpful visual way to think about this in a moment, but for right now, just trust me on this.
Of course, anybody buying a second-hand car, look out for those words. Charlatans say those words. Trust me. Okay.
Then we need to combine that insight with the observation that everybody sees the speed of light to be the same, no matter how fast they're moving with respect to one another.
Nobody sees the speed of light to be the same. People see light, don't see the speed of light.
Let's start with an analogy and then come back to relativity. To understand the analogy, you need to imagine a car driving on a huge flat surface.
Of course, we can never show you with like reality. We have to ask you to imagine things. Okay.
Further, you need to imagine that the car can only move at one speed, say 60 miles per hour. Or, so the comments don't fill up with metric snobbery hate mail, 100 kilometers per hour. Now, let's put a couple of arrows on the screen to point out north and east. While we know the overall speed the car is going, we don't know how much of it is in the east direction and how much of it is in the north direction. So let's take a closer look at that. The car can move entirely in the eastward direction, which means that it has no motion in the northward direction. Or the car can move entirely northward and not at all eastward. Or we can live dangerously and move towards the northeast. In this case, we see that the car is moving in both the east and north directions, with neither direction getting all of the motion. So that's the core analogy, and hopefully it's very clear.
That's the biggest load of gibberish I've heard. Yeah. So what's going on here? Car, traveling, speed. Great. What direction? This direction. Great. What's the confusion there?
Now, let's bring in relativity. In relativity, we don't have the east and north directions. Instead, we have space-time. Let's imagine that the horizontal direction is space and the vertical direction is time.
No. Objection. Why? Well, see how north and east are cardinal directions? And you can have those on a plane surface? Yes, right. Well, if you're going to say that time and space are equivalent to cardinal directions, then both of those will be on the same line. Not different lines, it will be the same line. Time, space, same material, great, same surface, just draw a straight line. There you go, there's space-time, one line, not two different lines at different angles. Yeah, you say space-time is the one thing, it's a fabric, great. Put it together and just draw one straight line, great. What's going on with the velocity? Dead easy, look, this is what's going on.
So suppose that there is a single and fixed speed that we can travel through space-time. This happens to be true, so it's not a ridiculous supposition. We can therefore mix these ideas with our...
Whoa. Now imagine that there's a single fixed speed at which we can travel. Yeah, that's right. You heard it here from this cosmologist. Listen.
And fixed speed that we can travel through space-time.
Got to go back. Listen.
Let's imagine that the horizontal direction is space and the vertical direction is time.
No, let's not. Let's imagine that the horizontal direction is space-time. Great. Continue.
So suppose that there is a single and fixed speed that we can travel through space-time.
So there's a single and fixed speed that we can travel through space-time.
This happens to be true, so it's not a ridiculous supposition.
Huh. Did you hear that? Yeah. We can travel through space-time, including you going from your house to the shops versus your pal who's going from his job to the airport. No, you're both moving at the same speed. Yeah, because you're both subject to the same space-time. Yeah, and you're both in the same world. You're both moving at the same speed. Yeah, because that's what this guy said.
We can therefore...
And to the detractors, you're moving through space. That's what motion, you need space to move. Okay, you're moving through space. Don't pretend that you're not. Like, he's not moving through space. Yeah, moving. It requires space. That's where it happens.
Mix these ideas with our earlier analogy. An object can move vertically. In that case, they're not moving through space, and they're moving entirely through time.
Oh, really? An object can move entirely through time, but not space. Well, that's not motion. That's right. Did you hear? It's not motion if it can only move. Yes, Gene, I am looking at a different screen to chat.
That's probably what you're doing right now. You're sitting and watching this video, so your position in space isn't changing. However, you are experiencing time. You aren't moving through space, but you're moving through time. On the other hand, what happens as you start moving through space?
Okay, screen frozen, you're telling me in the chat. Oh dear. Yes, I see. What's going on? And I'm now moving. Yeah, I can see in the thing. But what's right? Oh dear. Okay. Thanks for that, Gene. Let me see what's going on here. It's frozen. Yes, dagnabbit. Sorry about that, folks. It doesn't matter. You could hear what I was saying, but I will show the video. Wait, which one am I showing?
That's a fan.
I hope you could hear it. Why can't you go faster than light? There. Nabbit, why did that happen?
Fancy way to say that you gain some velocity. Well, we see here that what starts to happen is that as you begin to move through space, you move less through time. And eventually...
Wait. So let me just check. Yes, now you're all seeing what I'm seeing. And yes. Apologies for that, everyone. This system, Dagnabbit, I will get the hang of it sooner or later. So let's go back to him saying, yeah, no motion, but time.
Therefore, mix these items. There's a single and fixed speed that we can travel through space-time. This happens to be true, so it's not a ridiculous supposition. We can therefore mix these ideas with our earlier analogy. An object can move vertically. In that case, they're not moving through space, and they're moving entirely through time.
Wait a second. On the globe Earth, even if you're sat very, very still, you're moving through space because the Earth is rotating. So no, wrong. You can't just move through time because movement requires motion, and that motion requires a space in which to happen.
That's probably what you're doing right now. You're sitting and watching this video, so your position in space isn't changing. However, you are experiencing time. You are.
All the flat earthers are saying, wrong. We're moving 500 and we can roll out the various different speeds at which we're supposedly moving when we're not moving.
Aren't moving through space, but you're moving through time. On the other hand, what happens as you start moving through space? That's a fancy way to say that you gain some velocity. Well, we see here that what starts to happen is that as you begin to move through space, you move less through time. And eventually, when you move only through space, you don't move through time at all. And this...
When you move only through space, when does anything move only through space without time being a factor?
It's basically what relativity says. As you move faster and faster, your clocks slow down. And
right. Sorry, let me just thank everyone in the chat. And from now on, I will look at this screen instead of trying to monitor the other thing. Right, sorry about that. So I'm going to go back and we're going to listen to that gibberish. Yeah.
And as you space, well, we see here that what starts to happen is that as you begin to move through space, you move less through time. And eventually...
but wait a second. Isn't space also made out of time? Yes. Therefore impossible. It's like the road you're traveling on is made of space-time. And it's made of red and white bricks. That's right. And you can go very fast across this road that's made out of space-time. Yeah, but if you go really fast, you only hit the white bricks. Like, no, I think that's a gibberish. Sorry.
Actually, when you move only through space, you don't move through time at all.
Only through space. God, how do these guys get away with this?
And this is basically what relativity says. As you move faster and faster, your clocks slow down. And as you get very close to the speed of light, your clocks very nearly stop. We've scientifically proven that this is what happens, and I direct you...
They have not scientifically proven this, but let's see where he directs us.
...in my video on time dilation, so you can see one way that we've tested that. So...
we will go to that. We'll go to that video on time dilation.
So this brings us to our fundamental realization of relativity. The reason that we can't move through space faster than the speed of light is because we're constantly moving through space-time at a single speed, the speed of light.
Did he just contradict himself again? Let's see.
Faster and faster, your clocks slow down. And as you get very close to the speed of light, your clocks very nearly stop. We've scientifically proven that this is what happens, and I direct you to my video on time dilation so you can see one way that we've tested that. So this brings us to our fundamental realization of relativity. The reason that we can't move through space faster than the speed of light is because we're constantly moving through space-time at a single speed, the speed.
Yeah, remember the other one, the other video, where if you're surfing on a gravity wave, you can go faster? Yeah, if you're just a certain distance away from Earth, you're just automatically moving faster and faster. Not through space, but with space, because space is growing. Now he's saying, no, we're going through space and it's at a constant rate.
Speed of light. If we aren't moving through space, we experience time in the fastest way. And if we start moving through space, we experience time slower and slower. Finally, since we're moving through space-time at a single speed, that means when we're only moving through space, there's no more speed to gain. We move through space at the speed of light, and that's it.
Jeez, they do get away with this. Yeah, and that's it. Even though he just said you can't just move through space. Sorry.
Observation.
You can't just move through space, because any motion is through time too, see? But if you are moving only through space...
It wasn't made by Einstein. It was made by his mentor, Hermann Minkowski. Minkowski was one of Einstein's mentors, and he was a better mathematician. 2 years after Einstein's seminal 1905 paper, Minkowski appreciated the geometrical underpinnings of special relativity and had determined this deep and fundamental explanation why we can't travel faster than light through space. There are two final important points. First, while Minkowski showed why light speed is the maximum speed through space, what he didn't explain was why we move only at one speed through space-time. To this day, nobody really knows. It seems to be a fundamental property of space-time.
Nobody really knows. Doesn't know what? Well, the gibberish that I just said about space-time and motion.
Maybe we'll take another...
Yeah, nobody knows why. Could it be that it's not even happening, that it's just a made-up gibberish? Yeah, could be.
Person as smart as Einstein to figure out that particular conundrum. The second point is more technical, and I mention it only for the real physics nerds. In my analogy, I connected space and time as being similar to east and north, and there's a lot of merit in that. Morphing from motion through time to motion through space was like turning a car from moving north to moving east. However, this analogy is also technically inaccurate. From a mathematical point of view, it uses the geometry of circles, while the proper geometry is that of hyperbolas. I only bring this up because I want you to know my analogy is imperfect and you shouldn't push it too far. Otherwise, you might come to a numerically incorrect conclusion and think that you've made a new discovery.
Very funny. What he's really saying in a verbose way is, I should have used one line for a surface and a vertical line for sky, and say the car can move along the road or the car can go up. That's what he's talking about, a parabolic shape.
If you want to dig into this more deeply, be sure to use the full and proper Minkowski mathematics. Still, even with the limitations I've mentioned, the core point is valid. The reason that you can't move faster through space than the speed of light is because every object moves through space-time at one and only one speed, the speed of light.
Gee, apart from galaxies, yeah, and all of the objects inside those galaxies, yeah, they can move faster.
Once you embrace that central idea,
and they can move not in space-time,
and the fact that space and time are just like two directions of space-time, then all of those seemingly weird observations of relativity just click into place. And
that's right. As long as you can convince yourself to accept a retarded thought, then everything just clicks into place.
Special relativity makes total sense.
That's right. If you say anything retarded makes total sense, then all matter of retarded things will make total sense. Very good. Great. Now I think that's the end. Let's
So I don't know about you, but I think this insight about relativity is just about the coolest thing ever.
Oh, you're retarded, you, with your symbols. Let's go into time dilation. Let's see his thing on time dilation. Hey, where's the search thing? 1 second. Time dilation. Right, okay. So, yes, I am showing the right one. Okay. Here. Wait, before I go ahead, let's just make sure that this is the one that he was talking about. Yes. Okay. Here. So we're going to watch this one for educational purposes. Again.
Einstein's theory of special relativity has fascinated the public for about 100 years. People hear about clocks running at different speeds, objects shrinking, and a myriad of peculiar other effects. And people might be willing to accept those sorts of assertions, but when they start thinking about relativity, they come up with what seems to be paradoxes. Then they begin to doubt the theory because, well, paradoxes. One such paradox is the oft-quoted statement that moving clocks tick more slowly than stationary ones. This is the whole basis of the ideas of interstellar travel, where a person heading at high speed on a spaceship to a distant star ages more slowly than a person stuck on Earth.
So they go through less time. I wonder if all those people... I'm joking, by the way, Globlings, don't take this seriously. I wonder if all those people going from Santiago to Sydney, where it takes like 12 hours, as measured from the Earth, from an airport, for somebody going to pick them up, they're only really traveling for 10 hours inside the plane.
If that rings a bell, that's the basis of the famous twin paradox of special relativity. I'll actually make a video focusing entirely on the twin paradox, but in this video, I want to really drive home some math that shows you have to be ultra, mega, extremely careful when you claim that there's a paradox in relativity. So let's start with the most common time dilation equation you'll find in a relativity textbook. It is T sub moving equals gamma times T sub stationary.
In other words, gibberish times gibberish. Oh, okay, let's go then.
T sub moving is the time experienced by someone who sees the clock moving. T sub stationary is someone who doesn't see the clock moving, and gamma is a factor unique to relativity. It's called the Lorentz factor. It is equal to 1 for something not moving and greater than 1 when something is moving. Gamma is simply 1 over the square root of the quantity 1 minus v squared over c squared. That'll be important in a little bit, but for the moment, just remember that gamma is greater than or equal to 1. At this point, it's probably helpful for you to watch 2 other videos of mine, specifically the one on the derivation of the gamma factor, and the second one introducing Einstein's equations. I won't assume that you've seen them as I go through the rest of this video, but what I say here will be a little bit clearer if you've got those 2 under your belt. Okay, so let's get back to the time equation. What it says is simple. Given that gamma is greater than or equal to 1, it means that the time experienced by a person seeing the clock move is more than the time experienced by someone who doesn't see it move.
It's a bit like a watched pot never boils.
And this means that someone moving ages more slowly than a person who isn't.
Somebody busy, time appears to not affect them in the same way as somebody bored, sitting there looking at a clock.
Now this sounds crazy, but it's been proven to be true.
And by the way, Einstein said, yeah, time is relative. You see, if I'm talking to a pretty lady, time just goes like that. If I'm at the dentist, oh, it really drags.
I made a video about that as well. It's called Einstein's clocks. So this idea is behind a lot of science fiction, and it's true to a degree.
Wait, what? this idea is behind lots of science fiction, shouldn't you be saying, lots of science fiction is behind this idea?
But it's not the entire story. There are two key points I want to make here. The first is that this makes absolutely no sense. Not because it's...
So, let me tell you something that's just such a bunch of gibberish that it makes absolutely no sense, but I'll tell you about it anyway.
Two clocks tick at different rates, although that's pretty weird, but because of an ambiguity. Suppose you label the two people as number 1 and number 2. If we take number 1 as seeing the clock to be stationary and number 2 as seeing it moving, we see that number 2 experiences more time than number 1. However, relativity requires that the laws are the same, no matter who is not moving, and this poses a problem. Suppose that we say number 2 is stationary with respect to his clock, and number 1 says that the clock is moving. Then number 1 experiences a longer time. Okay, so this is a problem. If you pick person 1 to be the stationary with a clock, then person 2's clock ticks faster. If you pick person 2 to be stationary with a clock, then person 1's clock ticks faster.
Do you remember? I'm going to do it again. What he's actually explaining was in an episode of Sesame Street. Here, there you go. I was going to use 2 socks, but instead I'll just use my hands. And in Sesame Street, take opposite directions. Closer. How far away? Hey, you there. Huh? What do you mean you there? I'm not there. I'm here. It's a long-winded version of that. That's right. So this guy saying that guy, he could say, from this guy's point of view, that guy's next to a clock. From that guy's point of view, this guy's next to a clock. That's all it is. Don't get all crazy and confused, Globlings. That's all it is. From this guy's point of view, that guy is moving with a clock. And he could say, that guy is moving with a clock. From that guy's point of view, this guy is moving with a clock. Hey, you there. I'm not there. I'm here. You're there. No, I'm not there. I'm here. You're there. Do you see what I mean by it's retarded? It's for very stupid people. Ugh. Let's go back to it. I think this is the window. No, this is window. There you go.
And both people are equally right in saying that they're stationary.
And both people are equally right in saying, no, I'm here, you're there.
They can't both have clocks ticking faster than the other. That just makes no sense at all.
Yeah, the whole clock ticking faster bit is a little bit thrown in there. There's a bit of gibberish. Not ticking faster, ticking at the same pace. Yeah, from the clocks, if you had a camera fixed to each clock, never mind moving and not moving, it's like tick, tock, tick on both clocks. Yeah, not one's moving faster than the other. Not camera recording moving clock, camera recording still clock. Tick tock on both. Ha, good gosh, really? Yes, really.
Either we have logically proven that relativity is just bogus, or there's something more to it. Given that the scientific community still embraces relativity, there has to be something more to it. And
could it be that they're all a bunch of charlatans? Yeah, it could. All right, well, there's the answer.
The answer is both very subtle and technical. So let's dig into that. So, begin by putting up the most basic and general equations of relativity. These are called the Lorentz transforms, and they show how you can translate between the point of view of two observers who are moving with respect to one another. Ooh. Let's put up the time dilation equation I mentioned before as well. Notice that the Lorentz transforms have both a position and time equation. Oh. We're not interested in the position one here, so we'll get rid of it. And we'll change the symbols for the time one so it looks more like you usually see in the textbooks. So the first thing you see is that the time dilation equation is a special case of the more general one. They're the same, only if that extra term of v over c squared times x substationary equals 0. And
but wait a second. It's TSA just wrote in the chat. I think it was TSA. Let me just make double sure. Yep. Person, clock, moving. Person observing. Oh, clock's moving. But wait a minute. What if clock not moving and person moving instead? It would appear like clock moving.
that is true only if either the velocity v is 0 or x stationary is 0. The first one is pretty trivial, as that means that the two people aren't moving with respect to one another, and so you don't need relativity theory at all. But the second is a lot trickier. It says that the time experienced by the person seeing the clock moving depends both on the time experienced by the person not seeing the clock move and by the location in the frame of the person who sees the clock to be stationary. So that's a big point. What it means is that we have to be very careful about defining which clock we're talking about.
Remember, some time ago, there was I forget who it was, another cosmologist, talking about how brave the scientists were. Yeah, and remember how this guy, this is the second time, or the second video in which he said that you have to be careful. So, yeah, otherwise might explode.
There are many clocks stationary with respect to each observer. Since they're at different locations, we need to take that into account. Since this is a core point of this video, I want to explicitly show what this means. Let's start out by just talking about one observer, which we'll call number 1, who is stationary with respect to the clock. We draw him here with his clock. But that's not the only clock in his world. He has clocks at every location, and since those clocks aren't moving with respect to him, all of those clocks are ticking identically. Now let's add in observer 2. He sees observer 1 moving to the right at velocity v, and he wants to know what he thinks the moving clocks will read. To do that, we'll use the Lorentz transforms, but to do that, we need to figure out the locations. Let's pick 2 locations. Say the location of observer 1 and observer 2 as seen by observer 1. Observer 1 always thinks his location is x sub 1 equals 0. Since observer 1 thinks observer 2 is moving to the left at velocity v, he sees observer 2's position is changing. According to observer 1, observer 2's position is just x sub 1 equals minus v times t sub 1.
Oh.
Let's stop the motion and concentrate just on the 2 locations and times as seen by observer 1. His own location is simply x sub 1 t sub 1 equals 0 t sub 1. Now let's write down observer 2's location as seen by observer 1. It is just x sub 1 t sub 1 equals minus v times t sub 1 t sub 1. We can now use the Lorentz transforms for time. Let's first find out what observer 2 thinks the time is at observer 1's location. We just put in the values seen by observer 1. In doing so, we find that t sub 2 equals gamma t sub 1. That's just the normal time dilation equation. Now let's do the same thing for how observer 2 sees what observer 1 sees at observer 2's location. Remember that observer 1 sees this location as x sub 1 t sub 1 equals minus v t sub 1 t sub 1.
If you're not hearing the gibberish, like, I'm going to play it again. If you're not hearing the gibberish, there's no help for you and no hope for you. So listen.
Remember that observer 1 sees this location as x sub 1 t sub 1 equals minus v t sub 1 t sub 1.
Yeah. Oh, that's not gibberish. Oh, no, because it all means other things. Yeah, when a proper imbecile comes to you and goes, he thinks that has a meaning. He said,
we start with the equation t sub 2 equals gamma times the quantity t sub 1 plus v over c squared times x sub 1. We put in the x and t seen by observer 1. Thus, we get that T sub 2 equals gamma times the quantity T sub 1 minus V squared over C squared times T sub 1. So that's pretty easy. We can factor out the T sub 1 and get this equation here. And at this point, we can use the definition of gamma, which I remind you is 1 over the square root of the quantity 1 minus V squared over C squared. That means that this equation can be written as T sub 2 equals gamma divided by gamma squared times T sub 1. And finally, we get T sub 2 equals T sub 1 divided by gamma. That's divided, not multiplied by. That's exactly the opposite thing we saw when we looked at what was happening at observer 1's location. Now we need to step back and review a bit. This means that the transformation for what observer 2 sees compared to what observer 1 sees depends on the location. Observer 2...
The transformation? Oh, I almost split that in there, didn't you? Yeah, there's a transformation between what the one observer experiences and the other observer experiences. Yeah, there's a transformation between what two individuals experience. Yeah, there's a transformation there somewhere. Is it happening to subject 1? No. Is it happening to subject 2? No. Oh, but there's still a transformation. Is that yes?
2 sees more time elapsed than observer 1 sees at observer 1's location, but sees less time elapsed than observer 1 sees at observer 2's location.
Do we test that? Yeah. Go on then. Go and check it. No, didn't find it. Sorry.
This is a super subtle point, but it clearly says that comparing clocks between 2 moving observers is a tricky business.
So, now we have Skype. Now you can have somebody on Skype on a train showing his clock to an observer who's stationary watching that clock on their TV. What does the fact that you can't watch it like for miles and miles because like of sight, you're still watching a train and a clock moving? Oh, look, it's TikTok, just like your TikTok, moron.
You need to take into account both the time each experiences and the location at which the comparison is going on.
Remember, all of this is actually based on nuclear clocks. Yeah. Take 2 nuclear clocks. What's a nuclear clock? Never mind that. It's a nuclear clock. 2 of them at an airport. And you take one with uber care and you levitate it into the plane so that there's no moving or anything, no interference whatsoever onto the plane. You watch very carefully. The plane's already running, so it's not like they're starting up or the plane is having any impact at all on that clock. Flies around for 16 hours. Comes back, compare. There's a 0.00000000001 second difference. Oh, really? Do you check for this difference before you set off? But no, we just assume they're atomic clocks. Gonna be ticking at the same rate. Oh, right. And that's all true, is it? Yeah. Who says? NASA. Oh, okay.
Further, they both agree that the remote person's clock is slower. You probably need to think long and hard about this and maybe even rerun this video to get...
And brainwash yourself. Yeah, the other person's clock, it's slower than mine. Yeah, because I keep moving about.
Get your head around this idea. A crucial point here is that when people start grabbing equations from relativity textbooks without understanding exactly what the equations mean, then they'll almost certainly make a mistake. And perhaps the most important point is that you ever, and I do mean ever, find something about relativity that sounds weird to you, always go back to the Lorentz transform equations. They will never let you down.
Ah, that's why there's a transformation. Yeah, because it's a transform equation. You can't have a transform equation with no transformation taking place. Otherwise, well, nothing will be transforming. Right, so where's my thing? Here it is. And there. Now I'm going to join you in the chat. What a bunch of gibberish. But obviously, The Globelings will say, you just don't understand because it's very complex, Antonio, and you just don't understand. It's beyond you. Like, yeah. Remember the bit where he explained why you can't go faster than the speed of light, but how you can go faster than the speed of light? Remember that bit, Globelings? Because Globelings will do that. They'll say, well, I forget all about that stuff. That was complete, obvious gibberish. No, I'm going to say, fingers crossed, I think you don't understand it, Antonio. Oh, really? Did not strike you? That's so peculiar that I might have mentioned how in A Brief History of Time, Hawking explains how the faster you go, the more mass you accumulate. You just increase in mass because the more energy. Yeah, well, no, that's now false. But you're not going to stop to go, huh, he must have quote mined that. No, I just remember it from when I read the book when I was about 17. Dumbasses. Okay, John C. Oddity. Listen, any comment that where you're swearing, it gets blocked. So don't bother writing a comment that's where you're swearing because it just gets blocked. It does, nobody sees it. So just don't, don't swear. Simple. That goes to anyone who wants to swear in the chat because it gets held. And I have to either show or hide. And I can't be bothered going and showing comments where people say, this is just a crock of, because I'm going after my way to not swear. So I'm looking in the chat. Hey, so TSA's comment, which is there's no swearing there. Okay. Remember, Antonio, that 0.0000 is one perfectly fine for red's retardic. So he would just say that 1 second by 1,000 seconds is fine. There's nothing swearing there. So I'm allowing that comment. I don't know why that was even blocked. Yeah. Anyway, I'm scrolling through to see if anybody's written anything for me. Gleam, MMX expected 0.4, but only found 0.00113. So all Lorenz did was say, what do I need to do to turn 0.00113 into 0.4? Oh, yes, I remember this. I remember you writing about this to me a long time ago. I know, I will invent transforms to equate to 0.39887 minutes equals 0.4. Oh, there you go. Just transform what you have. So, and is that Mickelson Morley, MMX? So they do a test. They find something different to what they were expecting to happen. So Lorenz comes along and says, yeah, you see what you found, that's different. You see how that's different to what you thought it was going to be? It's exactly what you thought it was going to be. See, you just transform it into this. You say that 0.4 is this other number, and there you go. It's fine. I'm just scouring through the chat. Oh, so before, right at the start of this, there was this Zonk Jimmy says that you could hear it before when the video stuck because I hit the wrong thing. Thanks for that. There was a Globling in the chat, and apparently he wasn't getting enough attention, so he started spamming, just copy paste loads of globes and silliness. Like, well, if you weren't enjoying being here, why didn't you leave? No, I banned you. Estúpido. Oh, Perez. Anyway, so that was this Spanish Globling that I had a very quick debate about. He says, okay, this Globling says, oh, Danny Diesel, I just going to color copy the maps and mail them. No, Danny, don't. I will get the one that you pass me on eBay. That's what I'll do. Okay, so Danny Diesel, just save yourself the hassle and keep it. And I'll have one too, and we can compare if we want. So this Spanish globling, Hispanic, Cuban globling, bringing bad reputation to the Cubans. So he says he has confirmed Earth's drift with his Foucault pendulum by watching it swing for 10 minutes. That's right. He's then gone on to say that it doesn't actually make a circle, it makes an ellipse. And when I said to him, well, I didn't get to say, I was going to say to him, how do you know that you're not measuring a part of the ellipse? If it's making an ellipse, what makes you think it counts as a Foucault pendulum? Because the Foucault pendulum, in the mind of this globling, because he's not kept up with more advanced globlings who are also more retarded globlings, who say everywhere on Earth it makes a circle in 24 hours, because that's what a gyroscope would do if left in situ. A gyroscope would show, depending where you are, a turn of 360 degrees in a whole day. So they say, so that's what the Foucault pendulum does. Then along comes ICE to see an American woman who's I think she's a flat earther, but she's the truth anyway. Showing Foucault pendulum side by side, going, this one appears to be doing what it's supposed to do. This one doesn't. Oh, the one that appears to be doing what it's supposed to do, sometimes it stops doing it. The other one just fails all of the time. That's interesting. But according to the half-wit that was spamming in the chat, oh no, just 10 minutes, just swing it and just check for 10 minutes and say, yeah, there you go. That's what I'm expecting to see here. Oh, they're so stupid. They're so painfully stupid. Rune Thorson, it was a guy called Hugo Perez. Hugo Perez. It's in my previous hangout. It was in Spanish, though. So I'm looking in the chat. Scaries, who are you writing about? Chicken back. I don't see. Anyway, just trying to explain to somebody intelligent who has somehow convinced themselves that all of that relativistic nonsense is true, trying to explain to them, and you can explain it by like showing them physical objects. You can show them physical objects, say, look, what you're saying about space-time, show me with these two objects, okay? Draw whatever you need to on the table and show me. And when they show you, go, no, that's wrong. You're showing east versus north. That's what you're showing. No, I'm now saying, no. East versus north is what you're showing me. If you want to show this other thing, then you'll be doing this. One straight line for distance, space, and a vertical line for time without space. But it doesn't quite work, because if space is space-time, then there isn't anywhere that is just time or just space. It's just such a gibberish. Oh. Anyway. Right, folks, that's it. I'm going to bail. I need to practice more with that thing, this new system. I might just go back to OBS. But yeah. Right, folks, thanks for hanging out. And now I'm going to wrap up. And hope you enjoyed that. Yeah, you can't go faster than the speed of light. This is how you can go faster than the speed of light. You can't go faster than the speed of light. This is how you can go faster than the speed of light. Okay, so there you go. Thanks, folks. I will see you all. Shalom.